Okay, so here is an example of using a stack in an actual program. So the source code for this is actually posted on GitHub, and I will add it to the iLearn this week's material. Okay, so first let me show you what this program is doing. So if I do assemble and run, you see that is the output that I'm getting, 9876 all the way to 1. So what this is doing is actually is getting an array, so I can give it any array or any number, and so I can change this, and I'm telling or specifying the size of this array. And what it does, it's basically reverses this array. So if I print now again, you see that all the elements of this array is reversed. And it's not just printing um, in a reverse order. So it's not doing that, like it's reading from this direction and going and printing them. It doesn't do that. It actually reverse the elements in the memory. So I can show you, if I take this code out and do run. So here you're actually seeing in the, as we talked about, this is your data segment, or basically what we put in this data segment. And you see that if I change this address or the values to seeing decimal, you see that these numbers are here. So these are array. So you see 1, 2, 3 all the way to 9, and then 100, 101, 200. And basically they are stored in memory. So if I come back and put this code back that I cut, and I do assemble and run again, you see that it's actually the order is changed in the memory. So we didn't just like iterate through it in a different order. So we actually updated the location of each of these basically in the memory. Okay, so how this is done, basically we are using the stacks to get these things done. So that's one basically one feature of a stack that you can use. So let's say if I have an array of 1, 2, 3, and I am pushing every element to the stack. So I do first, so let's say this is my stack, there is the top of the stack, and first I push 1, and then the next element 2, and then the next element 3. So this comes on top. And then if I do pop until basically all the elements are out and save them in a location, I'm gonna get that elements in a reverse order. So if I now do pop and save them somewhere, gonna be 3. So that's gonna go out from the stack. And then I go pop one more time. So we'll get 2. And the next time we're gonna get 1. And that will be pop. So you see that we change this 1 to 3 to 3 to 1. So that's how we are using the stack. Okay, so how the code is actually doing this now. So there are 3 parts. We have a loop, loop 2, and loop print. So I want to actually rename this. This is, I'm gonna put it a push loop, and here, and this is a pop loop or loop pop. So the whole code is actually divided into 3 sections. This part, this loop, is responsible for reading every element. So it's going to iterate through the array and push it to our stack. The second pop, this part, is responsible for going through that same memory locations, so same memory addresses that we did as before, but this time, instead of reading, it's gonna pop one element from the stack and save it to that memory location. And then this last one, it is going to go through the same memories again. So for the third time now, it's gonna go through the same memories, but this time it's just printing the numbers, and that's how we get this output here. So that's the big picture. So first we push the elements to the stack, all of them, and then we pop all of them, and then we print from the memory. So at this point, actually our stack is empty because everything's already popped. So let's look at each of them in more detail. So first we are doing getting that addresses. So I have the size and array being stored in S0 and S1. So as you see size, we are doing a load word because I'm reading a single number. So I'm reading this 12 into S0. For the address, I'm doing a load address. So I'm getting not the first element, but the address of the first element. So that is what we are doing here. And then here, since we're gonna be working with these two numbers, and I intend to change these numbers, I'm just making a copy of them. So I'm putting S0 into T0, and I'm putting S1 into T1. And that is just to preserve this so later I can use them again. I could use this one again instead of doing this. Just a style preference. Okay, so now let's look at this loop. So what is important, I'm going to put a note here also that this is 0, T0 is a size, and then this is address of first element. Or I'm going to put current element because we're going to be updating this T1. Okay, so what happens here? First, we are doing a load word, and we said that load word is basically reading from the memory and storing it into a register. So that means I'm giving the address. I have to give the address of the location that I want to read from. So this is what I have here. And basically it's gonna save, currently is the first element, into T2. So here it's gonna basically save number 1 into T2. Then I am saving that number to the stack. So I have the value of the, let's say, the current element, and I want to save it on a stack. So the way we do that, it's basically as we explained in the slides. We are using save word, and that's because we are saving the register's value to the memory. So that T2 here is the value that we are saving to our stack. And we are doing an offset of -4 from our stack pointer. So the stack pointer, we talked about it, that the stack pointer is always referring to the current element or the top of the stack. So that means at that address, so if I had this, I would be overriding some content that is on the stack. So that's why we do -4. That means the next available spot. And then we have to update that stack pointer. So it's basically pointing to the new top of the stack, which is the new number that we have. So now basically that's the two-step that we take to save something to a stack. We always write the value and update the stack pointer. So at this point is basically our main job is done for pushing something to the stack because we loaded the value and saved it to the stack. The next step is to move these pointers and counters that we have, so basically we can move to the next element. So we have two things here. One is T1, and that was the current element, so the address of the current element, and I am adding 4 to that. And the reason is we are here dealing with a word, and each of them are 4 bytes or 32 bits. So I'm going to go to the address of the next element. So that means by adding 4 to that, it's basically skipping the 4 byte for this element, and the pointer will be located for this element. the next thing I'm doing is I'm reducing 1 from this size that I had. So I'm using this size actually as a counter um, to know when to exit this loop. So it's gonna start at like 9 or 12 in this case, and it's gonna keep decreasing one by one, basically all the way to 0. So once it's at 0, we are checking here, and if basically it's greater than 0, I'm gonna go back to this loop. But once it gets at 0 or smaller, it's gonna exit this loop. So that is how basically I'm keeping track of this um, this loop. So I want to get this code out and run this, but this time I'm going to run it at a smaller step, so maybe 4 instructions per second. And one more thing, that here if you look, there is kind of a handy drop down that we can go to the, for example, they have different things, but one of them is a stack pointer. So to the current stack pointer. So it goes on the memory and shows me what is on the stack. So if I actually assemble and run it and go to there, which is already there, it by the way jumps on its own, but whatever is changing. So you see that these elements are being added to my stack. And you see that it's going from the higher address to the lower address. Okay, and another thing that you can run it slower, or you can do a step also. So at any point you can, basically if you go back, and there is no speed limit, but then here you can go one by one. So you don't have to actually do the play, you can do one line by one line and follow the code. And here you can see the stack pointer also. So if we get this back to hex values, you see there's a stack pointer here. So that's one of the registers that we talked about, and that is the content or the current location that is pointing to. And if you look at this address, it's basically matching with this, and it's ending with F4, which is basically here right now, because that is E0 and this is plus 10. So that's going to be F and, well, actually it's pointing here. So it's 1, 4. So it's F and 4 here, the last two, because it is plus 1, 4. And I think if I go one more, yes, it's going to be F0 now. So now it's pointing here. So you can track that actually what is happening with your stack pointer. Okay, so if you go back, so basically that was the first loop. So that's the push. I put the code back, and this is the second loop. So here after this condition that we had, I am basically repeating this code that I had up here and getting a fresh copy from basically my, I think this was the size and address of the current element. Okay, so now in this part we are going to pop every element from our stack. So we already have that 12 element in the stack, and I'm going to pop one by one as we are iterating through the array and save that number to that location in the memory. So we are basically updating these values. And if you go back here, you can see that obviously the first thing that we need to do, because we want to write this number on our array, is going to be popping that number from the stack, basically to get that number first. So this is again a two-step process. So the first thing is that to do a load word, because we are reading from the memory and writing to the um, a register. So this is the location that we're going to be reading from, and I can remove this 0, it's not going to change anything. So there is a location that we are reading from, and we are always reading from the stack pointer in this case. And we said that makes sense because we said that the stack pointer is always pointing to the top of the stack. Like that's the convention that we should use. So we can safely assume that there is a number stored in that memory location that the stack pointer is pointing to. So we are getting that number and we're putting it in T2. And then we are still not done with the pop operation because we have to update the stack pointer. So we know that that number is not on our stack anymore. And we simply do that by basically incrementing the stack by 4. And again, 4 is 4 byte, because we are dealing with numbers. Each number in MIPS is represented with 4 bytes or 32 bits. So this is basically our pop operation. So now we have the number in our T2, and I'm going to save that number to the array. And how we do that? Now it's in the different direction. That means we are reading from our registers, which is T2, and writing it to a memory address. So T1 here is coming from here, which is the address of the current element. So if you remember, we had S0, S1 here as a load address of this array. So it's the first element at this point. Okay, so this one basically writes that element that we have from the stack back to our array. And basically that's the main part again, but we have to update the counter. So we are moving to the next element, and basically this loop is working. So the way we do that, we just add 4 to our current element pointer. So T1 is our current element pointer, and I'm adding 4 to that basically to go to the next element. And again, doing a -1 here from our counter, so we can stop our loop at some point. And I encourage you again to run this one by steps so you can see what is happening. So I'm gonna take this last one out, and let's run that again and see what we can see this time. So if we go at maybe more this time, and so first we're gonna see that is basically we are loading this number into our stack. So I'm gonna slow it more down here. So here you see that I put these values back. So you see that it is updating the value in the array. So we are in this data section right now. We are not in the stack pointer. And you see basically it's rewriting those values. And one thing to add about the way the stack works. So if you actually click here and go back to your stack pointer, you see that the stack pointer is putting the hex back, pointing at this address ending with FC, and that would be here. Yeah, and this is E0 plus 1C, so it's actually pointing here. So that is where the stack pointer is pointing. But you see that the numbers that we had are actually there. They did not get erased or anything. So the reason is that we are just moving the stack pointer and we are not actually resetting these values. And that is how it's done. So resetting those values is going to be kind of like an extra operation that is not necessary. As long as your stack pointer is pointing, let's say to here, we know that anything after or anything that is lower address than this, it's basically garbage or some data that is we can basically overwrite. So that is the reason that all these values are there, but we are not actually gonna use them. And from our point of view or from our perspective, they don't exist. Okay, so let's look at the last part. So here we have the print loop, and there is nothing new here actually from last week's. So this is going through the original array, and it's gonna print basically every number and then a space, and then the next number and then another space. So how we do that? We are first resetting these. So now I have so T0 was the this was the size, and this was address of the current element. So here first we are basically getting that element, so using T1, so that is pointing to the current element, and we are doing a load word to get that number here, so we have it in T2. These three lines are responsible for printing the number, so we are passing this print int from here, not number 1, so that's a system call for printing a number, and we are putting the number that we want to print in A0. So this is basically exactly it's always the same when we are printing a number. And then we are printing integer, printing a string, which is that space character here. So that is defined, the space is defined here. So you could change this one with anything. And so that's basically the first two here. And then after that, it's just the same, updating the counters to move the pointer to the next. So adding by 4 and updating the counter by -1 to basically know when to exit this loop. So we are checking that counter here, that T1. And then we are just exiting. So nothing new here. And if I run this for the last time, we see that I'm gonna go at the full speed, clear this. We see that we are getting this reverse array printed. So that's it for this example. This is basically a example of kind of like practical or more practical example for using stack and the push and pop operation.